Hello, my name is Amog Mandhalkar and I will be taking a tutorial on the use of Matlab to simulate interference. We'll go over the concept of interference once, then over the theory, what equations we are going to use, and then I'll show you how to simulate using Matlab. The concept of interference is fairly simple. The interaction of two coherent beams at a screen is called an interference. Now, what does this mean? A beam is called coherent when the phase relationship between the electric fields at different values of location or different values of time is fixed. Then it is called as coherence, which basically means if the value of phase at two different locations has a tight correlation or has a fixed relationship, then it means then the beams are coherent in space or are spatially coherent. If the phase relationship between the beams at different times for the same location has a tight correlation or has a fixed relationship, it is called as temporal coherence. Now, the best way to imagine it is in terms of a Young's double slit experiment. As you might know, in the Young's double slit experiment, we have first a screen after a source, and then we have two slits and then a screen. So what this experiment essentially does is it takes one single source and splits it into two coherent sources. So this is the best way to imagine it. Now we will go over the theory. What we want is two beams which we want to interfere. So consider the following equations. E1 of R and T is given by this first equation right here. We use an omega t term to show its frequency. This k dot r is the direction and phi 1 is the initial phase of the beam number 1. For the second beam, we have the same frequency and same direction but a different phase. Interference is basically the sum of both of these electric fields at a screen. Now, intensity is the square of the electric field amplitude, as we all know. Then the interference equation is this one. I is the total intensity, I1 is the intensity for beam 1, which is E1 square, I2 is the intensity for beam 2, which is E2 square, and then there is a term delta in this equation, which is basically the difference between the initial phase of beam 1 and beam 2. Now let's consider this example here. Consider that I1 is equal to I2 is equal to I0, which means both the beams have equal intensity. And let us also consider that omega t and k dot r for both beams are the same. So the only thing different for both the beams is phi 1 and phi 2, which means there will be a non-zero delta term, but everything else will be the same. So what does the interference equation look like? It is I is equal to I1 is equal to I2 is equal to I0. So 2 I0 plus again 2 into I0 into I0's whole root. So again 2 I0 into cos of delta. This is what it would look like. We'll see what happens when we plot I with respect to delta. There's at delta equal to 0, the value is 4 I0, keeps dropping as delta increases. It goes to 0 at delta equal to pi, for which cos is minus 1, and then again it increases, and when delta equal to 2 pi, then again goes to 4 I0. That is the variation. So the variation is essentially around 2 I0, and it goes from 0 to 4 I0. Now we will have a look at how to simulate this particular example that we just discussed. What we do now is use the Matlab editor to write a program for this. we use these commands to clear any data that was already present in Matlab. Now we create two variables to denote the limits of x and y direction, because what we essentially want to look at is a two-dimensional view, that is a cross section of a beam. So it will look like an image. That's why we have to give a 2D representation. So say x goes from minus 0.5 to 0.5 with a step of say we want 100 steps. So 1 by n minus 1, we will define n, we have to do it before x, plus 0.5. So say we want 100 points by 100 points, so we give value like this. And the reason we give x as this value 0.5 to 0.5 with a step of 1 by n minus 1 is that because the first element is going to be minus 0.5 and the last element is going to be 0.5, and we want 98 elements between them. So that is why, and the last element, since it is 0.5, we have to give such that after 0.5 there have to be 99 elements, and that is why. And then we want the y to be the same as x, so instead of putting the same statement again, we just put y equal to x. So now it represents y in the same way. Now what we do is we use a command called mesh grid, and the syntax for this command is we give the variables which we want equal to mesh grid x and y. Now what this mesh grid command does is it creates ordered pairs of x and y, and we can represent any function we want using these capital X and Y variables. Now what we do is we define E1 is equal to exp, which is the syntax for exponential function, and as we discussed here, the omega t and k r values, k dot r values are going to be same for both the equations, so we neglect both of them and we just give a phi1 value to the first field and a phi2 value to the second field, and both of these are phase terms. So what we do in our Matlab program is we give it the amplitude as 1 for both of them, which we want the same, and we give an exponent of 1i, which is which denotes a complex exponent which we want, and then we give it first one as a value of 0, just consider 0 as a reference, and for the second wave E2, what we do is we give it a different phase value. So we give 1i multiplied by, so now because we have discussed a constant phase but a different value, I'll give it a constant phase of say pi by 3. Now in order to implement this interference equation in Matlab, we can use the following syntax like I will explain now. Let us consider E is the field, total field. It will be E1 plus E2 dot multiplied by, we use this dot multiplied by because we want term wise or element wise multiplication of two matrices, and the second matrix will be conjugate or complex conjugate of this sum E1 plus E2. Once we take the this multiplication, we will have our interference diagram ready. Now what we want to do is we want to plot this E function, but since it's an image, we don't use the command plot, we use image scan, and the way it is done is in this way. So first we give the command to create a blank figure, the command is given figure, then we say image scan, and in the argument we put E, and then because we want the plot to be in black and white scale, so we do a color map and we specify the color map that we want, it's gray, and because we also might want to look at what value a point has, we also want a reference or a color bar to be on the side, so we use this command color bar. Now we run the entire program. I'll just save it as test interference, and now we have a field with constant phase or constant intensity all over it. And if you want to have a look, what we can do using Matlab is we can use tools, a data cursor, and we can put a data cursor anywhere. So it is showing RGB equal to 0.5, index is 3, which means this is the value that it is using. It is showing 3 all over the area. So which basically means that the entire area of the interference pattern has the same value, and the value is 3. Now this was a fairly simplistic example, and it didn't really show any spatial variance in the phase values. So the next example that we will look at, it will be slightly different. So an interference simulation, again we'll define two beams. Both beams will again be plane waves. That means constant electric fields with planar wavefronts, but there will be one key difference here. Again, both the amplitudes will be the same, but one beam will be tilted with respect to the other. Now what that means is explained in this schematic. Now the red beam is the first beam which is coming normal to the screen, and the blue beam is the second beam which is coming at a certain angle with respect to the normal, and that angle is given as theta. So I'll just represent it again. So say we have a screen here, and we have one beam coming normal onto the screen, and the vector is like this. The wavefront is going to be perpendicular to the direction of propagation. So this is the wavefront. And the second beam that we have is coming at a certain angle. And again the vector I'll show like this. This is the angle theta. And the wavefront for this beam is going to look like this, perpendicular to the direction of propagation. This angle is again theta. Now what if we choose a point here, say this point, this distance is y, and what we see here now is that at this particular point, which is at y distance from the bottom point, the beam, the blue beam has traveled a little extra distance, which means it has gathered extra phase. How much extra phase it has gathered can be given by this particular equation that I will just write down. It's 2 pi by lambda into y cos theta. So as it happens, as you go up from the bottom point, the phase keeps accumulating, and as we know, after the value of 2 pi, the phase can be considered to be again jumping back to 0. So what happens is, the way we see the phase varying over this plane is something like this. It goes from 0 to 2 pi, goes back to 0 again, it goes to 0 to 2 pi, goes to 0 again, and goes 0 to 2 pi, and this keeps happening. So this is something which is called in the language of Matlab as wrapping of the phase function. It is being wrapped around 2 pi. So what we want to do now is simulate this particular interference. Now the way we do it is, I'll show you on the Matlab editor itself. So again, what we do is we consider these very similar syntax as previously, and since we want one of our beams to be normal to the screen, we let the E1 equation stay the same. For the E2 expression, we use a different formula, and for that we will need to specify a few things first. First will be, we specify the value of lambda to be, say, 0.633, which is the wavelength in micrometers for a red laser. Then we specify the value of k, which is equal to 2 into pi by lambda. Now we also want one more thing, which is the tilt angle and theta. For our purposes, we'll use theta as pi by 3. We could use any angle, but pi by 3 is a reasonable guess, or a reasonable value to consider at the start. Now what we will do is, for E2 we will change the expression to exponent of 1i multiplied by k multiplied by x, because we want the variation to happen in one direction, multiplied by cos of theta. Now what we should see is an interference pattern which will contain fringes. That means there will be black and white fringes along one direction, which is the x direction. Now we'll plot the entire variation, or plot the entire interferogram. So this is how it looks like. Now there's only one key difference here, that there is a black region on both sides, and then there's a white region in the middle. Well, there is one more way in which we can I can show you the fringes in a better way, and that is, I'll just write another program in case it is not very clear. So we use again the same syntaxes, x is equal to, but now I'll just change the a few values here. We'll consider n equal to 100, like we mentioned, 100 pixel by 100 points by 100 points image. X is equal to minus 1 to 2 by n, or n minus 1 in our case, actually n minus 1 to plus 1. Y is equal to again x, which we want the same values. Then we use again the same command, xy is equal to mesh grid of x comma y. And now what we do is we define L again as our wavelength as 0.633. Then we define k is equal to 2 into pi by L. Then we define our theta as equal to, say again, pi by 3. Now there will be one key difference here, is that E1 is again going to be exponent of 0 into x plus 0 into y for our program. And the second beam, where we want a variation in phase along one direction, what we do is we use exponent of one I into k into x into cos of theta. Now we again have the equation ready. Now what we do is we generate a figure, use the figure command to create a blank figure. Then we put an image scan of E. Oh, I have not defined the function E. I just realized. E should be equal to E1 plus E2 dot multiplied by, which signifies the element wise multiplication of conjugate of E1 plus E2. And now we have the equation E ready. We use the image scan of E, then we use color map as gray, then we use the command color bar to give a color bar in the side so that we can refer to what the value is. And we will run this program. We'll say tilted interference Now it shows us this interference pattern. Now what we can do here is play with the tilt angle, that is theta. I'll just make this angle as pi by 6 and run the program once again, and as you can see, as the tilt changes, the number of fringes that appear changes. Now what if I change it again to say pi by 10? The tilt angle is again changing, so the number of fringes that we see will change. The next thing that I would like to do now is to show you what happens if we take this plot and we select one particular point and we see what variation is happening along the direction of change in the fringe pattern. So for that we have to use a plot command, since we are taking one particular line and seeing what's happening along that line. So what we will do now is generate another figure, and we will now say plot the 50th line of the E, and since we want to plot the entire line, the second variable we do not want to do anything to it, because we want to plot all points along the second variable. We just put a colon in there, which means the 50th row in E, all points will be plotted. Now we will just run the program once again, and this is what the variation looks like. So along the 50th line, along the 50th row, we travel in the x direction, and this is the variation that we see from 0 to 4 to again 0 to 4 and 0. So this is, like I mentioned, for an interference of two beams with equal intensity, this is what the variation will look like, 0 to 4. These are the basics of interference, and what you can do now is use slightly more complicated beams in order to simulate some different kinds of interferences.